Section 1. The Invisible Lifeguard. Earth's own shield. Our planet has an invisible lifeguard. It is a magnetic field. You cannot see it, you cannot touch it, but it is there, all around us, all the time. This field is generated deep inside the Earth's core. Liquid iron flows and churns, creating a huge, powerful magnet. This magnet creates a bubble that extends far out into space. This bubble is called the magnetosphere. It is our first line of defense against the harsh environment of space. It is one of the key reasons life, as we know it, can exist on this beautiful blue marble. It works silently, constantly protecting us from dangers we rarely think about. The sun is not just a gentle source of light and warmth. It constantly blows a stream of charged particles called the solar wind. This wind is powerful enough to strip away a planet's atmosphere over millions of years. Earth's magnetic field stands guard against this. It deflects the solar wind, guiding the particles around our planet instead of letting them hit our air directly. Without this shield, our atmosphere would be slowly eroded into space. Our oceans would evaporate. Earth might look more like Mars does today, cold, dry, and with a very thin atmosphere. Our shield is what keeps our world habitable. It is a fundamental part of our planetary life support system. Imagine standing outside on a clear day. The air feels calm. The sky is blue. This peace is possible because of the magnetic field. Section 2. The Cosmic Gauntlet. Dangers beyond our sky. Once you leave the protective bubble of Earth's magnetosphere, you enter a different world. Space is not empty. It is filled with a constant hail of tiny, invisible bullets. These are high-energy particles. Some come from our own sun, especially during violent outbursts called solar storms. We call these solar energetic particles. Others, called galactic cosmic rays, are shot out from exploding stars and other violent events far across the galaxy. These particles travel at nearly the speed of light. They carry so much energy that they can punch right through the skin of a spacecraft and the bodies of the astronauts inside. Navigating this is like running a cosmic gauntlet. For the human body, this radiation is a serious threat. These particles are like microscopic cannonballs. They can pass through your cells and damage your DNA. On a short mission, a sudden burst of radiation from a solar storm can cause acute radiation sickness. The symptoms are nausea, fatigue, damage to the immune system. On a long journey, like a trip to Mars, the constant exposure to galactic cosmic rays adds up. It increases the risk of developing cancer later in life. It can also damage the central nervous system and other organs. Section 3. The limits of our current armor. So how do we currently protect our spacecraft and our astronauts? The primary method is simple. We put a lot of material between them and the radiation. This is called passive shielding. Spacecraft like the Orion capsule modules on the International Space Station have hulls made of aluminum. We also use layers of other materials, like polyethylene, which is a type of plastic. These materials work by brute force. When a high-energy particle hits the shield, it collides with the atoms in the material and loses some of energy. The goal is to slow it down or stop it completely before it reaches the crew or the sensitive electronics inside. This approach has worked reasonably well for missions close to home. It provides a decent amount of protection against lower energy particles, like those from some solar flares. For short-duration missions, the total radiation dose can be kept within acceptable limits. We can also use storm shelters on the spacecraft. These are small areas with extra thick shielding where the crew can gather during a severe solar storm. The water supplies can even be arranged around the walls of these shelters. The food supplies can even be arranged around the walls of these shelters. It is a practical, low-tech solution that adds a layer of safety for the crew. However, this brute force method has a major drawback for deep space exploration. To stop the most powerful galactic cosmic rays, you would need incredibly thick shields. If a heavy physical barrier is not the answer, what is? The best ideas often come from nature. Scientists and engineers are looking at the one thing we know works perfectly: Earth's magnetic field. The goal is to create a miniature magnetosphere, an artificial magnetic bubble that can surround a spacecraft. This is called an active shield. Instead of blocking radiation with mass, it uses the power of magnetism to deflect charged particles away from the ship. Since most of the dangerous radiation in space is made of charged particles, protons, electrons, a strong enough magnetic field could steer them away before they ever hit the hull. The most promising way to create such a field is with superconducting coils. Superconductors are special materials that can conduct electricity with zero resistance when they are cooled to very low temperatures. This means you can run a huge electrical current through a superconducting wire without it overheating. By wrapping these coils around a spacecraft, you could generate a powerful and stable magnetic field. This field would extend out into space around the ship, forming a protective cocoon. Any charged particle that tried to pass through would be bent away on a new trajectory, missing the spacecraft entirely. Another exciting idea that works alongside magnetic fields is the plasma shield. Plasma is often called the fourth state of matter, after solid liquid gas. It is essentially a gas energized so much that its atoms have been stripped of their electrons. This means it is a cloud of charged particles, ions, electrons. Because it is made of charged particles, plasma can be shaped and controlled by magnetic fields, electric fields. The idea behind a plasma shield is to create a cloud of this ionized gas around the spacecraft and hold it in place with magnets. This cloud would then act as an additional barrier against incoming radiation. The plasma shield would work in a couple of ways. First, the dense cloud of charged particles could help to deflect incoming radiation particles through electrostatic repulsion, pushing away particles with the same charge. Second, and perhaps more importantly, the plasma itself can help to shape and strengthen the magnetic field that contains it. By injecting plasma into a magnetic shield, you can effectively inflate the magnetic bubble, making it much larger and more robust than what the superconducting coils could create on their own. A bigger bubble means the spacecraft is better protected as particles are deflected much farther away from the hull. While the concepts of magnetic plasma shields are incredibly promising, the path from the laboratory to a flight-ready system is a long and difficult one. There are immense engineering challenges that we still need to overcome. The first and biggest hurdle is power. Generating a magnetic field strong enough to deflect high-energy cosmic rays requires a tremendous amount of electricity. A spacecraft on a Mars mission would likely rely on large solar panels, a small nuclear reactor for power. A significant portion of that power would have to be dedicated just to running the shield, leaving less for life support, communications, scientific instruments. The second major challenge is mass and complexity, particularly related to the superconducting coils. To work, superconductors need to be kept extremely cold, just a few degrees above absolute zero. This requires a sophisticated cryogenic cooling system, complete with pumps, radiators, and insulation. All of this equipment adds mass, cost, and complexity to the spacecraft. It also introduces more potential points of failure. A failure in the cooling system would cause the coils to lose their superconductivity, and the magnetic shield would instantly collapse. Building a system that is both lightweight and reliable enough for a 3-year mission to Mars is a monumental engineering task. Despite these difficulties, progress is being made. Every year, our computer models become more powerful and more accurate. They allow engineers to refine their designs and find more efficient configurations that require less power or a less complex cooling system. Small-scale prototypes have been built and tested in labs on the ground. These experiments, even if they are not full-scale shields, provide invaluable data. They help us understand how the materials behave, how the fields interact, and where the weaknesses in our designs are. Each test is a small win, a step forward on the long road to a working shield. The future of testing may lie in smaller, dedicated missions. We could imagine sending a small, uncrewed satellite, perhaps the size of a CubeSat, into a high-radiation orbit to test a key component of the shield technology. It could test a new type of superconducting coil, a more efficient cooling system, a plasma injection method. These smaller, more focused tests are less expensive and less risky than building a full system for a crewed mission right away. They allow us to learn and iterate in the real environment of space. Through this steady, incremental process of modeling, ground testing, and small-scale space trials, we can gradually solve the challenges one by one. Solving the radiation problem is not just an academic exercise. It is one of the essential keys that will unlock the next chapter of human exploration. A reliable and effective active shield would fundamentally change our relationship with deep space. It would make long-duration missions safer, not just possible. Astronauts could travel to Mars and back, a journey that could take up to 3 years with a significantly reduced risk of radiation-induced health problems. They could spend more time on the Martian surface conducting science, searching for signs of past life without constantly worrying about their accumulated radiation dose. It would transform Mars from a destination for a daring few into a place we can genuinely explore. The benefits extend far beyond Mars. The outer solar system is home to some of the most fascinating worlds we know of, like Jupiter's moon, Europa, Saturn's moon, Enceladus. These icy moons are thought to have vast liquid water oceans hidden beneath their frozen shells, making them prime candidates in the search for extraterrestrial life. But the radiation environment around Jupiter in particular is incredibly intense. A mission to Europa, especially a crewed one, is almost unthinkable with today's shielding technology. A successful magnetic shield, plasma shield, would protect not only the astronauts, but also the highly sensitive scientific instruments needed to study these worlds. We are not there yet. A fully functional spacecraft force field is likely still decades away. But the work being done today in laboratories and on supercomputers around the world is laying the critical groundwork. Continue to push the boundaries of materials science to create better superconductors. Refine our engineering to build lighter and more efficient power and cooling systems. Keep testing our ideas with increasingly sophisticated models and prototypes. Each breakthrough, no matter how small, brings us one step closer to our goal. This is a challenge worthy of our best minds and our most persistent efforts. Ultimately, this is about the future of humanity. We are an exploring species. From the moment our ancestors walked out of Africa, we have always been driven to see what is over the next hill, across the next ocean. The solar system is our next ocean, and space is our next frontier. Building the tools to survive out there is a natural continuation of that journey. Just as early sailors learned to build ships that could cross the seas, we must learn to build ships that can cross the void between planets. An active radiation shield is more than just a piece of technology. It is a vessel for our hopes, a tool that will help us carry the human spirit safely to new worlds. Sometimes, during a powerful solar storm, you can see the shield at work. The particles it catches are funneled down toward the poles. They collide with air molecules and create the beautiful auroras. Northern lights, southern lights. This light show is a visible reminder of the powerful, invisible battle being fought high above our heads every single day. It is our planet's way of showing us the shield that keeps us all safe. We have to figure out how to bring our own lifeguard with us. That is one of the biggest challenges for the future of human space exploration.